2.1 explainer. A particle's position is described by the function Vx is equal to kt squared meters per second, where k is a constant and t is in seconds. The particle's position at 0 seconds is negative 9 meters, and at 3 seconds the particle is at 9 meters. We are going to determine the value of constant k and be sure to include the proper units. Our goal is to determine the value of constant k. We will need to use the integral of velocity. Why derivatives and integrals are important is we need derivatives in physics to show how something changes. We use derivatives to find instantaneous accelerator or velocity. We can use integration to add many things together quickly. Integration gives us an area under a curve, while the derivative is the slope of the curve. In the universe, quantities are almost never constant, so we must use derivatives and integrals. Here's an example of like our particles: velocity, time, its position, time, acceleration over time. So velocity is the derivative of velocity with respect to time. So if vt is equal to the derivative of s, then the change in s is the integral of velocity x dt. So change in s is equal to sf minus si. So 9 minus negative 9 is equal to Vx dt. So we can just write that as 9 equals 9 plus, since velocity is equal to k times t squared, we can write k t squared dt, and we'll put a bound of 3 to 0. So integrals, the formula, so we want to integrate that t to 2, and we know x n plus 1 over n plus 1. So our t will be, kt is going to be integrated to be t3k 1/3. So now we know that 9 is equal to 9 plus 1/3 kt3. And so we want to bound this to find how much k is equal to. Put it on the bound of 3 to 0. And we can just plug in, so 9 is equal to 9 plus 1/3. 1/3 k times 3 to the third minus 1/3 k times 0 to the third. 0 to the third. We just cancel that out. And then we'll get 9 is equal to 9 plus 9k. Oh, sorry, this is this should be negative 9, because not 9, negative 9, so it will be now 18. We distribute 9k, which k is equal to 2, and that is our constant k.